Justin Moresco was the project manager of a recent ATC project. And Justin, I'll ask you to introduce yourself a little bit more, but really appreciate you and your ATC team being here today. As I mentioned, one of those stepping stones is to characterize damage to this particular category of structure. And ATC has done a tremendous amount, some of it with us, really filling in the answers on that stepping stone to resilience. So Justin Moresco, with an apology for that slip, I'll now turn it over to you. Thank you very much.
No problem. Thank you so much, Janelle. Good morning, everybody. As Janelle said, I'm Justin Moresco. I'm a director of projects with the Applied Technology Council, and I just want to thank Janelle and the rest of the CEA team for this opportunity to present on 3 recent ATC projects. What I'd like to do before I introduce the first speaker is just talk a little bit about each of these projects, in particular about why I think they bring so much value to the practice of earthquake engineering and more broadly society in general. I do want to remind everyone, as Janelle mentioned, that we welcome questions, but we're going to wait until the end of all 3 presentations before we respond to them. There we go. Okay, moving forward. So here's the 3 projects that we're going to be talking about. Two of these showed up on Janelle's stair steps. The one at the top was not on the stair steps, but you'll see soon why it is relevant for today. This was the ATC 116 project, Solutions to the Short Period Building Seismic Performance Paradox. It resulted in 4 reports, the FEMA P2139 reports. Those actually haven't been published. We expect that they'll be released in another month or so on the FEMA website. The second project, ATC 110, Vulnerability-Based Retrofit Solutions for Dwellings. This resulted in the FEMA P1100 series of reports. Those are all available on the FEMA website. And then third, the ATC 143 project, Guidance for Assessment and Repair of Earthquake Damage to Residential Buildings. That resulted in 2 reports, the CEA EDA 01 and the CEA EDA 02 reports. Both of those are available on the CEA website and also the ATC website. So, each of these projects is a unique application of earthquake engineering, but at the same time, there are some commonalities, some sort of through lines among the 3 projects. And so I just wanted to talk briefly about that. The first is that they all either exclusively focus on, or at least have a major focus on wood light frame construction, what would typically be, you'd see out there for single family dwellings and often for multifamily dwellings. The other sort of through line is that these projects influenced one another. So for example, the ATC 116 numerical modeling of wood light frame buildings influenced the numerical of the ATC 110 wood light frame buildings. And that, I understand, that numerical modeling from ATC 110 in turn influenced the peer CEA project that we're going to, the modeling for that project at least, that we're going to hear about later today. And then the physical testing data of wood framed assemblies that were collected for both the ATC 116 project and also the ATC 110 project in turn influenced the repair recommendations for structurally significant damage in the reports that came out of ATC 143. Okay, so let me just talk a little bit. I've got 1 slide for each project, and then I'm going to introduce the first speaker. But starting with ATC 116, Solutions to the Short Period Building Seismic Performance Paradox. There's been a number of analytical studies over the last 10 years, which have predicted much higher collapse rates for low-rise buildings, a range of structural systems, not just wood frame, that are commonly used for low-rise systems. They predicted collapse rates that are much higher than what has been observed in historical earthquakes, particularly Northridge. And at the same time, many of these predictions actually were pointing to collapse probabilities that are higher than what are the limits that are targeted in current building codes. So, for example, currently risk category 2 buildings should not have a probability of collapse given really strong ground motions, or for those of you who are earthquake engineers are familiar with building code terminology, for ground motions, MCE ground motions should not be higher than 10%. But in many cases, these predictions, these analytical predictions were that collapse rates were much higher than that. And so that led to some important questions. One is, okay, are these numerical models pointing to problems that we just haven't observed? Or is that there are shortcomings in these analytical efforts? And so, really what this project is about is looking at the reliability of codes, our current building codes, and the reliability of new buildings that are being constructed to those codes. I don't want to spoil the answer to those questions. I'm going to let the presenter speak to those later, so I'll just move along. But I do want to say that's going to be answered. And also there were two really, I think, important findings that came out of this project. The first is that in order to accurately model wood frame buildings, you really need to consider the contribution of non-structural walls to strength. And sort of related to that is that a major reason why wood frame buildings have performed well in past earthquakes is because of the non-structural walls. So these are walls that are sheathed with, like, say, have plaster or stucco. And then the last point there, the other sort of second kind of highlight that I wanted to point out that you're going to hear about more later, and that is that our ATC 116 models were finding that buildings that were designed and then subjected to really strong ground motions, the type of ground motions you'd only expect to see near fault, had much higher probabilities of collapse than buildings that were designed and subjected to strong ground motions, MCE level ground motions, but far away from faults. And this is contrary to the intention of the code. The code says, okay, if you're at a site that's close to a fault, we're going to expect much higher forces. Those higher design forces then should lead to greater strength in the design of the building, and that greater strength should sort of level the playing field. But that's not what we're seeing, at least in our 116 models, and we think this is something that deserves further investigation. The next project, ATC 110, vulnerability-based retrofit solutions for dwellings. Even though wood frame buildings have performed very well in past earthquakes, as Janney was pointing out, there's still thousands of older buildings out there that have these known structural vulnerabilities, like unbraced cripple walls. And so the purpose of the ATC 110 project, which led to the P1100 series of reports, was to make retrofit of these known vulnerabilities easier and more cost effective. And the hope is that that would then lead to many more of these buildings being retrofit, which in turn increases the probability that these homes can be used for shelter after a major earthquake. The documents establish a methodology to identify and retrofit known vulnerabilities. They also provide plan sets. This is a picture of one here to the right, which include prescriptive pre-engineered retrofit schemes with the hope that this will then lead to easier and more cost-effective retrofits. And then volume 1 of the P1100 series is a pre-standard, and the expectation is that that would serve as the basis for eventually for an ANSI approved consensus standard, which if that's achieved, that would then lead to hopefully more broader dissemination of these retrofit schemes, and also mainstreaming of these practices into engineering practice. And then the third project that we're going to hear about is ATC 143, Guidance for Assessment and Repair of Earthquake Damage. Even if all the old buildings out there with these known vulnerabilities were retrofit according to FEMA P 1100, we still expect that there's going to be a very large number of homes that are damaged, many of them severely damaged after a major earthquake, particularly centered in an urban area. And so this project really is about providing guidance for assessing that damage and repairing that damage, which in turn we hope should lead to a quicker recovery and greater reliability of those repairs. The documents provide a systematic and comprehensive methodology for documenting that damage and making decisions about repair based on that damage. They provide information about earthquake versus non-earthquake caused damage. There's some guidance on when to do destructive investigations, for example, to identify if there's been structural damage to components that are concealed, like wood framing behind sheathing. And you only want to do this when it's really necessary, because of course it's costly and it's disruptive to the occupants. And then lastly, these guidelines provide common and efficient repair methods, which we think is going to lead to more cost-effective repairs. So that's just a high-level sort of summary of all three projects. Hopefully that's sparked your interest. And so with that, I'd like to move on and introduce our first speaker. He's going to be talking about the ATC 116 project. Weichiang is a professor of intelligent infrastructure at Clemson University. He was he was a member of the project technical committee for the ATC 116 project, and he oversaw the numerical modeling of wood light frame archetypes for the 116 project. So over to you, Weichiang.
Thank you, Justin. As Justin mentioned, my name is Weichiang Peng. Sometimes I go by Peng if easier. Since I did my graduate study here in the US, my fellow colleague and student, they just call me Peng here. So as Justin mentioned, I oversaw the development of the numerical model in ATC 116 project for light frame wood building here. And I'm a professor at Clemson University in Clemson in South Carolina. So I'm one of the percentage show up in the earlier survey from the East Coast. I'm glad to join many of my West Coast colleagues. So ATC project actually cover 3 different types of construction type, including light frame wood building, masonry, and also steel frame structure here. But in my presentation today, I will focus on the discussion for wood building, in particular residential building. So this is the project team. Obviously, I didn't analyze all those buildings by myself or design it. Charlie, he's the technical director for the project. He oversaw the entire operation. And Kelly Cobeen on our technical committee. We have Professor Daniel Dolan as well in our technical committee, and Professor Andrea Filatro. And Jim Harris actually helped us design the archetype building, residential building, which I'm going to present later on. And myself, Weichiang Peng, I oversaw the development and analysis of all the light frame wood structure. We also have a project review committee, build home, field line, and Steve Pryor from the industry, providing us review and technical guidance. Lisa and John Stewart gave us input on soil structure analysis problem. And we have woodworking group, my student Urshad Ziad and Maria, they help us perform the analysis. So with that, I think Justin showed this kind of figure before. This plot pretty much sum up the issue we were trying to solve. So in the FEMA P695 project, the summary can be seen on this graph here. The vertical axis show the probability of collapse for the structure. Go back here. Oh, I think I screwed up thing here. I'll just try to kind of bring up the drawing option here. Let me see. All right. So I just want to point out that the vertical axis shows the collapse probability, all right, under the kind of design level event, what we call the maximum considered earthquake. Maximum considered earthquake. As you can see, the horizontal axis show the period of the building. From this plot, it can be seen that as the period reduces kind of below 0.5 seconds, we see a spike or increase in the probability of collapse. So this kind of imply for all those code compliant building, we would observe a much higher collapse rate for short period building. So for building that with period of 0.5 seconds or less, typically building in the order of 5-story or less, 4 or 5-story or less, let's say 1 and 2-story single family home.
Hey, Peng, this is Justin. Sorry to interrupt. Your volume is not coming through so loud, at least for me.
Okay.
So
is it better now?
Yeah, that's
right.
better.
Maybe I need to just holding my mic closer to my mouth here. All right, thank you. So this is a so-called kind of short period building performance paradox. So why do analytical model of code compliant design predict much higher probability of collapse for short period building, contrary to our observation right after earthquake? So as this famous quote I heard from Bill Holmes, "Show me the body," because right after all those like major earthquake event, we just did not observe that many structural pancakes collapse for short period building. So there is some discontinuity here. This means there's a so-called, this is what we call a paradox. So for the ATC projects, as mentioned, the main objective here is to come up with a practical solution to the problem we observe for short period building. When I say the problem, it's mainly the numerical model provided unrealistically high probability of collapse in the P695 study here. So as part of the objective for this study, we study the light frame wood building, and we want to investigate what are the causes resulted in the paradox, and also develop practical solution to address the paradox. And the other objective here is to improve the analytical model. This means the computer model we use nowadays to predict structural collapse. And we want to use a computer model and calibrate it to full-scale shake table tests. We have some full-scale shake table tests available since the P695 project. So at the end, one of the objectives for the project was to provide basis and recommendation for design practice, obviously with the input of the design community, if anything we need to change for the design code. So in this picture here, I think Janney shows some of the picture. This is a picture of, these are two pictures of single family dwelling damaged right after the earthquake. As you can see, there's large lateral displacement or drift, right? If you look at this, this is maybe in the order of, I'll say more than 5% drift, perhaps close to 10%. Similarly, you see this another older 2-story home, with a large drift here. The building will be ragtag. However, this is not so-called collapse yet. We don't see the pancakes collapse, right? Here is two pictures of apartment building. So, for example, right after the 1994 Norwich earthquake, the Woodland Hill apartment building, the first story actually pancakes collapsed. What you can see here for the upper story, the second floor and so on, it is pretty much intact. Same here, you could see that the second floor and above pretty much intact. However, the first floor kind of collapsed, right? So that is one other important observation here. So most of the lateral drift we observe in the first story, and then upper story, there's very little signs of damage. Moving on here as well, and this is another picture, kind of quite famous picture from the 1989 Loma Prieta earthquake. You could see that the story above pretty much intact, with the first floor experience very large lateral drift here. If you just look at the picture, judging from it, again, I think we are looking at about 10% lateral drift. Right? However, the building did not collapse in terms of structural pancakes collapse. This another picture show the 2-story full-scale wood building tested in Japan. This is right after 2 Takatori earthquake. You could see the first floor is pretty much trashed or damaged. The drift is in the order of 10 to 20%. Again, we see the same behavior. Second floor is pretty much intact. So these are a few major observations from either the actual damage after earthquake or full-scale shake table test. Now, so Charlie actually looked into all those data collected after the 1994 Norwich earthquake and then passed them into different census tract and look at the number of ragtag. We use ragtag in this project. We use ragtag as a proxy to estimate so-called collapse. We recognize that sometimes ragtag data does not represent the actual pancakes collapse. However, this is the best data we have. So from all the data, after you can see the plotted trend line, horizontal trend line, and then versus the horizontal axis is the shaking intensity, right? So the spectral acceleration, you can think of that as a shaking intensity. Vertical axis is the actual count of the collapse rate. Broadly speaking, for the MCE level, 1.5 G, if you read here, this is the so-called maximum considered earthquake. We are looking at somewhere around near 5% collapse rate. This is from the field data. Right. So this provided us a kind of target benchmark for the actual collapse rate we observed in one earthquake, the 1994 Norwich earthquake. Right. So I'm going to summarize some of the key observation. All those collapses for light frame wood building, the collapse mode is pretty much P delta side sway collapse in the first story. So this exclude some of those failure due to ground foundation issue. All those without foundation issue, we pretty much observe side sway first story collapse. This is also the same behavior we saw in the full-scale shake table test, right? This kind of confirmed the failure mode. And then the upper story, the lateral displacement is limited inter-story lateral displacement. We also observed that at incipient collapse, the building can actually sustain very large displacement in the order of 10, even 20% drift prior to actual pancakes collapse. This is also, again, confirmed through the shake table data here. Very low probability of collapse was observed in the actual earthquake here. Charlie also passed out the data, look at those wood building with ragtag. He grouped them into 1-story building and also 2-story and taller. So from the data, we could actually see that for 1-story building, the rough collapse rate count is about 2% or less at MC level. For 2-story or taller wood building, it is actually closer to 5%. So we observe a trend of taller the building, you have higher collapse rate. So keep in mind, this become our benchmark, 2% and 5%. One is for 1-story, the other one is for 2-story and taller. So in this project, we actually cover all the kind of possible design space using something called the archetype building. We group the building type into something called a commercial building. We have 1, 2, and 4-story building, and then multi-family dwelling, namely apartment, 1, 2, and 4-story as well. And we also look into single family dwelling, 1 and 2-story. For the single family dwelling, we actually have engineer design. We also have a conventional design based on a conventional design career. When we say the engineer, that means we are using SE7. At the time, we use SE710 design provision here. We consider different seismic design level. One is called a very high seismic, and the other one is called high. Very high seismic is referring to those buildings located kind of near the fault line in a very high seismic zone here. We also look into moderate. However, in this presentation today, I'm going to just mainly focus on very high seismic and high seismic region here. In this presentation, since we are focusing on residential building, I'll pay more attention to multi-family and single family building here. The only difference, the main difference in the commercial building here is for the building, we have a much more open floor plan. Inside the building, there's not as many partition wall compared to multi-family apartment building. So this kind of slide kind of show the rendering of the three different construction type for commercial building. As you can see, there's much more open space with the orange color wall here. Those are the structural wall. Similarly, for the multi-family dwelling, you could see that all these are the so-called structural wall, right? It's been the engineered structural wall. For other, those are non-structural wall, what we call non-structural. That's mean we only treat those based on functionality. It is not prescribed and designed by the structural engineer. Similarly, for the two-story home, same thing. We have structural wall versus non-structural wall. Right. So for the analysis purpose, we use a program called Timber 3D. It is a research tool developed at Clemson University. This is not a commercial program. It's a research tool here. So this program can actually capture the nonlinear dynamic response and seismic collapse mechanism of 3D wood light frame building. We use core rotation formulation in our model, and it can actually use something called a large displacement theory. What it means here is the model can actually physically track the movement of the wall diaphragm and then observe actual pancakes collapse. As you can see from the animation here, we can actually track the floor diaphragm, how it dropped down physically, and then kind of crash onto the floor here. For modeling purpose, we use something called a simulated collapse. If you compare to the FEMA P695 project, which was completed more than 10 years ago, the project used something called a non-simulated collapse. All right. The project used non-simulated collapse where the lateral drift more than 7% drift is considered collapse. Right. So in the Timber 3D model, we have different elements. We use a concept called the building blocks. So to normalize, to simplify the modeling and design, we consider shear wall in the increment of 4 feet increment. Right? And as I mentioned, we use something called a simulated collapse, track the roof and floor diaphragm movement, and then there's no predefined collapse drift limit. In FEMA P695 project, there's a predefined 7% drift. And anything more than 7% drift is considered collapse. So to have a sanity check here, we have the full-scale shake table test data from the E-Defense shake table test completed by Professor Isoda. The building actually subjected to 3 Takatomi earthquake here. As can be seen, the second Takatomi earthquake did not collapse the building. The third Takatomi earthquake actually collapsed the building here. So to kind of calibrate our model, we actually created a model for that particular shake table test. What you are seeing here is a shake table animation of the numerical model using Timber 3D. The first Takatomi motion shook the building, and however, the building did not collapse. And as we move on to the okay, so as you can see, the building did not collapse, right? Right now, we are actually entering into the second Takatomi motion. You will see that the building already partially damaged. You will see much more inter-story drift in the building, right, in the animation. So what we observe here is the building did not collapse here. As the building is subjected to the third Takatomi motion, you will see that the numerical model actually predict collapse in the building. Right. So I'm not sure you can kind of see the red dot is kind of moving. So the third motion, Takatari motion, actually collapsed the building. So this kind of gave us confidence in our numerical model. So we use this. So in the modeling approach, we use something called the residual strength model. This is the hysteretic loops in the residual strength here. So what you will notice here, the end here, you're going to see a plateau, right? A plateau is defined in term of the ratio of the peak strength. The peak strength is Fx here. Right. So we can adjust the residual strength to 30%, 10, or 0% to investigate the influence of non-structural element. So this is simply to account for those non-engineered elements. For modeling purpose, we consider OSB low, high, and all those different sheathing arrangements. For example, you have 6 inches on center nail, 3 inches, and 2 inches, and so on. And this kind of slide show the actual backbone strength for different sheathing material or shear wall. And we have stucco and siding, which provided some strength here. However, they are not as strong as the structural wall, right? For analysis purpose, we perform 3 different analyses. Modal analysis to figure out the natural period of the building. Then we perform pushover, push in 2 of the lateral direction to figure out the strength versus displacement response. Then we apply something called a nonlinear time history analysis, actually put earthquake to shake the building, and then observe the different performance of the building. Using this information, we can come up with something called a collapse fragility curve. So this is one example to show the natural period of the building for a 4-story apartment building is about 0.5 seconds. This is on the higher end of the natural period for a 4-story building. And then this slide shows the pushover strength of a wood building with and without P delta effect. What I mean here is without using the gravity load. As you can see, without P delta, the pushover curves show a much higher strength at large breadth here, including P delta, it actually push it down. So this is much more realistic behavior. In the prior P695 project, P delta effect was not considered. So that is one of the different. Next year, we performed something called an incremental dynamic analysis. As you can see here, for different earthquake, each earthquake, we kind of incrementally increase the strength of the earthquake and track the maximum inter-story drift displacement. At some point, the displacement will keep increasing. At some point, you will reach something called an incipient collapse point. If you increase the strength, you will see pancakes collapse of the building. That means the displacement is very large, right? So all those red dots represent the incipient collapse point. We also quantify the average displacement at collapse and also the average strength at collapse, the shaking intensity. So at the end, we can build something called a fragility curve. So from the fragility curve, we can read out what is the performance of the building. For example, here at a design level earthquake, for the very high science peak, we observe something around the 28% collapse for this particular building. So in this study, we consider different parametric study, the baseline configuration, the effect of displacement, and also the non-structural element. What I mean by non-structural element, this means the gypsum wall board and stucco and so on. Other study, I won't talk about it. If you are interested, you can read it in our ATC report here, in the FEMA report. So this is a summary result we obtained here. If you look at here, this is a predicted probability of collapse, right? At MC level versus the period of the building. We observe the trend of, as the period increases, the probability of collapse actually increases. For shorter building, 1-, 2-story single family home has a much smaller period. We observe very low collapse probability. So this is also kind of in line with the benchmark for 1-story building, which I previously mentioned is like 2% collapse rate, and 2-story and larger is about 5% or even larger. That's what we expected. So this kind of solved the so-called paradox here. If you recall earlier, we have a U-shaped kind of response here. Now, using this new information from our project, actually we bend the curve. We actually saw probability of collapse increases as period increase. The other thing we also observe here is the actual strength, the over strength, right? The over strength. When you account for everything, not only the structural wall, also the non-structural wall, that's in the gypsum wall, but stucco and everything. For those single family home, there's a lot of partition wall, multi-family home as well, you have a lot of partition wall. The actual strength is very high. As the strength increases, the so-called true strength increases, the probability of collapse reduces. So that is another observation we came out from our project here. So if you look at very high seismic and very high seismic and high seismic performance, broadly speaking, this dashed line shows us the probability of collapse of those buildings located in very high seismic zone versus building located in high seismic zone. We saw a shift in the performance. That means for a given structure, if you design that the building located in very high seismic near fault zone, for some reason, even though you increase the design, we saw higher collapse probability compared to the counterpart of located in in a high seismic zone. Right? That is another key finding. I think this is worth further investigation. This bar chart simply kind of summarize the same information. High seismic versus high seismic counterpart, we always saw the increase in the probability of collapse. For single family home, we have much lower probability of collapse compared to multi-family and taller building. The other observation is as the number of story increases from 1 story to 2 story to 4 story, there's an increasing trend in the predicted probability of collapse. So in part of the study, we want to investigate what are the influence of displacement capacity. We artificially increase and reduce the so-called residual strength from 30% down to 0% and 60%. As you can see from the pushover curve, as the residual strength increases, we have much more displacement capacity. For example, here, this is collapsed at about 7% roof drift if you have 20% residual strength here. If you have 0, we can expect around 4% roof drift to have collapsed. So this show that this is a result showing our baseline. This is our best estimate. If you assume like 30% residual strength, the average collapse is around 12% interstory drift. Versus if you use a very conservative estimate of residual strength, that means there's no non-structure and other contribution, 0% residual strength here. The collapse, the interstory drift at incipient collapse is very low, about 4%. This does not match the observation in post-earthquake recognition and also full-scale shake table test, which we observe something in the order of 10 to 20% before pancakes collapse. So,
hey, Peng, this is Justin. Just wanted to let you know that we're going to have to transition to the next speaker here.
Okay.
In about 30 seconds.
All right. So in summary, I'm going to kind of to jump to the final summary. I think I only have a few slides. So at the end, I think what we observe here is non-structural element important. It's very important, right? So we need to account for non-structural element. And also the other observation here is the collapse displacement capacity is very important. If you use a very pessimistic estimation of collapse capacity, you are not going to get the result that match the reality. The other thing here is the P delta effect is important. The previous study in the P695 did not consider P delta effect here. And one other finding here, as I mentioned, for the very high seismic building, the building located in very high seismic, for some reason, even though we design for higher capacity, we still observe much higher collapse rate compared to those buildings designed in the high seismic zone. I think this topic warrants further investigation. Right? I think that's all I have. Justin?
Yeah, excellent. Yeah, thank you so much, Peng. Do you want to move forward if you could, just one more slide, and then there we go. Yeah, and then I think Kelly should be transferred control. So thank you, Peng, very much. Our next presenter is Kelly Cobeen. She's going to be presenting on ATC 110. She is an associate principal with Janney Elstner Associates in their San Francisco office. She was the co-project director for the ATC 110 project. So take it away, Kelly.
Thank you very much, Justin. Can you hear me okay?
I can.
Okay, great. And let me get the slide deck moving here. Beautiful. So I am incredibly pleased to be here this morning talking about the ATC 110 project and the FEMA P1100 documents that came out of that project. And as I go through, hopefully I'm going to be reflecting a little bit Justin's leveraging recent advances in engineering and what Janelle mentioned about using best available science, because we were very much thinking about both those things as we move forward with this project. Acknowledgements, a huge thank you to the California Earthquake Authority and FEMA for the funding behind it. And next, a quick acknowledgement of a very large team of people that were vital to this project moving forward and its successful conclusion. And I won't go through all of the names on the screen. A big shout out to the Applied Technology Council and their project management staff there. I would like to mention that on the project technical committee and the working group, we had a wonderful mix of engineers that were working in and very familiar with retrofit. We had a contractor helping us out, keeping us real. And very importantly, we had a large group of numerical modeling experts, and Peng was one of them, and he was working with a graduate student, and we had Dan Dolan working with a graduate student and Andre Filiatro working with a graduate student. And that was because we were using analysis very much like Peng was just talking about in order to figure out what the best retrofit was going to be and what kind of performance we were going to get out of retrofit. So that's the best available science part of this, and the ATC 110 project did very much benefit from the work that Peng and others had just been doing in the ATC 116 project. And we started with their modeling and we moved forward into this project. So quickly, the ATC 110 purpose to promote public safety and welfare by reducing earthquake-induced damage to existing wood light frame built dwellings. And the public safety and the reduction of earthquake damage are very much at the heart of the missions of the California Earthquake Authority and FEMA. And so this was trying to really be on point with that. The intent was to provide simple and systematic procedure to identify and retrofit vulnerabilities. And big emphasis on the simple. And as we talk about the products that came out, I will talk about how we envision simple and move forward with that. And to set a retrofit scope based on best available science. The big picture is, and I think this was very much something that California Earthquake Authority was thinking about. They really wanted one definitive resource to provide guidance for assessment and retrofit. They wanted one place to point at, because at the point where we started this project, the resources were kind of scattered, and you went one place if you were thinking about cripple walls and another place if you were maybe thinking about hillside dwellings. Definitely looking to facilitate implementation as broadly as possible, to set a method and to set the minimum retrofit level. The scope of the FEMA P1100 documents that are the result of the project are for wood light frame, primarily focused on 1- and 2-family dwellings, but also usable for townhouses with some limits. And if you're going to go and do cripple walls in retrofits in townhouses or assessment, you want to be doing all of the townhouse units within the townhouse building. So some things that way. Single family dwellings divided into multiple dwelling units were included. A lot of times we're talking about older houses in our cities that were initially a single family dwelling and built that way, but have been divided into multiple units. And seismic design category B through E, it can certainly be used across the entire range. The ATC 110 project, as we sit here today, really is complete. And the only exception being that there's a small amount of ongoing effort around developing training materials. But the project is complete, and the first and major document, I should say, that the project came out with is this volume 1. It is a systematic step through retrofit, or both assessment and retrofit provisions in a single document, also including very extensive commentary. It was written in pre-standard language with the idea that it would be developed into a standard. And in fact, ICC just last week kicked off the standard committee that is going to take this pre-standard and turn it into an ANSI conforming standard that can be referenced in the building codes. So this is a primary source of information, and even if you're using the other products, it's worthwhile to go back and look at this and to get advantage of the very extensive commentary that it contains. There are 3 sets of plan sets. These are intended to be used for the most part by the contractor to design the retrofit and obtain a permit without an engineer being involved. And that goes back to what was said about simple. We were trying to keep implementation as simple as possible in order to get as broad implementation as possible. And so we've got plan sets for crawl space dwellings, living space over garage dwellings, and masonry chimneys. Finally, for the people at the technical geek end of the spectrum, myself included, there is volume 3 that has background documentation. It has a wonderful example of implementation of a hillside dwelling retrofit that is of interest. It has lots and lots of different white papers that explain in detail what was done in the project and why and how. So quite a resource there. So one question that comes up is, why are we so focused on retrofitting 1 and 2 family dwellings? And I think Janelle gave a very nice introduction of what we're looking to do there, along with the other initial speakers. And one of the things that we realized is that for the most part, dwellings, wood frame dwellings, have an incredible track record of being very high performers in terms of safety. They may still have some damage, but they're very high performers, and they're very common across the United States. However, every single earthquake that we see here in the United States reminds us that there is a subset of those dwellings that has vulnerabilities, and those vulnerabilities can lead to significant damage and dwellings being uninhabitable following earthquakes. And so we recognize that, and we recognize that we really can do very practical things to improve that outcome. And so what we're doing is we're looking at vulnerability-based retrofit. We are not going to try and retrofit the whole dwelling. We're not going to try and bring it up to current code, because the dwelling overall really is a good performer. But we're going to focus on the vulnerabilities, and what you see highlighted here is a house with cripple walls, similar to some of the pictures you've seen so far. And we're going to focus on those cripple walls, and we're going to try and really get rid of that vulnerability so that overall the house performs a whole lot better. It is the most cost-effective. It is the least disruptive to the residents of the dwelling. And the only caution is we aren't going to be damage-free. It's not going to eliminate damage, but it's going to reduce damage, and it's going to increase the likelihood of being habitable following the earthquake. So what is included? There are really 4 major things, vulnerabilities that were addressed by the ATC 110 project and the FEMA P1100 documents. The first one is crawl space dwellings with cripple walls. And we have looked at this before, and there will be quite a bit more discussion about crawl space dwellings with cripple walls. They have vulnerable cripple walls, and they often have vulnerable bolting to the foundation. So as you see on the right-hand side, the dwelling can fall off of its cripple walls, or it can slide off the foundation. And the concepts of retrofit for this have been around for a while, and they tend to, for the most part, include putting plywood on the cripple walls, making sure that we have connectors tying the top of the wall into the dwelling above, and making sure that we have connections tying the bottom of the wall to the foundation. And that retrofit concept continues through this. Something certainly known but not as often addressed in retrofit discussion to date is hillside dwellings. These are dwellings that are built out over steep hillsides. And in the photo you see right here, this particular configuration has very, very tall cripple walls. And we found out in the '94 Northridge earthquake that these can be vulnerable to very significant damage and collapse, and unfortunately, in one case, loss of life. And so we're working with concepts that are going to better tie the lowest framed floor of this dwelling into the uphill foundation, keep it from separating from the foundation, and therefore keeping it from collapsing off and down the hill. The third vulnerability that's included is living space over garage dwellings. Very, very common in our housing stock out there. And you can really readily identify these because at the front of the dwelling, where you would like to have nice, sturdy shear walls or other bracing elements, you tend to have very narrow piers. The fact is that these are just another occurrence of the soft story, where in fact the whole story of the entire house or a wing of the house is very weak and vulnerable to damage, just like the apartment buildings that are getting a lot of attention across California and are the subject of some mandatory retrofit programs. So we've looked at retrofits that would improve the performance of those dwellings. And the final vulnerabilities that are kind of paired together are chimneys and fireplace surrounds. Even at very moderate levels of ground shaking, we do start seeing damage to chimneys, and have seen that in, I believe, every West Coast earthquake that we've seen over the years. And so the concepts behind retrofit of these often involve removing portions of or all of the masonry chimney in order to put back UL rated flues and light framing and create a safer result. So the FEMA P1100 document really steps you through three basic steps. The first is around determining eligibility to use the documents, and then eligibility to use prescriptive pre-engineered provisions or the plan sets. The next is around assessment. Does my dwelling have this vulnerability? Does my dwelling need this retrofit? And then finally, design and detailing of retrofit. So that's sort of the scope conceptually that it addresses. The primary objective is reduction of hazard to the occupants, improvement of safety for the residents of the dwelling. The work that's done inherently reduces the level of damage without eliminating it. And it's looking at target performance as close as practical to that used for new buildings, but not necessarily getting all the way there. The retrofit methodology used extensive nonlinear time history analysis, the numerical studies, just like Peng was talking about, and identified performance objectives as part of that, and balanced a desire to have as high performance as possible with a check of constructability to make sure it could practically be implemented and it would be desirable to implement it. We looked at a variety of different materials of construction because there's a lot of variability in the built environment. And we investigated a wide range of retrofit. And this is a little diagram here to talk about what we were doing. We developed performance criteria. We'll talk about that in just a second. We developed the methodology to design the retrofit, and then we did some trial retrofit designs. We had model buildings, we did a variety of levels of retrofit, and we turned it over to Peng and the other numerical modelers who went through analysis, just like Peng was describing, and came back and reported to us what the analysis said about the performance of the retrofit. And then we went into constructability and sort of a loop through all of that in order to try and optimize what we were looking at. As part of this effort, we had to understand the existing building stock, and part of it was the modeling parameters that Peng was talking about that we developed in order to go into the numerical studies that were really doing earthquake simulation, if you will. And a shout out to Colin Blaney, who was co-project director and did a very deep dive into old building plans and materials of construction and helped us build a really good idea of what the existing building stock and the ranges of strengths you see plotted here, varying strength over construction year, and other things that occur out in the building stock, so that we could understand the full range of the performance before retrofit and the full range of the performance with retrofit that we might be improving it to. I'll speak only briefly about performance criteria. We had a primary one, and just like Peng was discussing, it related to the probability of collapse in the risk-targeted maximum considered earthquake, a very rare earthquake. That was used because that is the kind of description that our building codes currently target for seismic performance. And so there is a stated probability of collapse that we try and target for new buildings, and there's an appreciation for existing buildings maybe hitting a slightly lower target. In addition to that, we added a couple of targets, secondary performance criteria that we're looking at level of repair and continued occupancy, and what we might be able to glean about those as we went through the analysis. We had to come up with a design method, and we basically went to the equivalent lateral force method as the simplified engineered design method, because it's what everybody in the engineering community is using on a very regular basis for new buildings. It is the simplest approach we have, and we thought that we could make good use of it. And we basically have created performance-based solutions by pre-judging the performance with all of that numerical modeling. So we had a simplified way of implementing it, but it has a performance basis behind it. Out of all of this, we developed a lot of plots like you see here. We got from our numerical modelers lots and lots of data, and we all sat together as the large group and looked at this data and made decisions about where to peg retrofits. In this particular case on the vertical axis, just like you were seeing in Peng's, you can see probability of collapse in this very rare maximum considered earthquake. And then towards the left-hand side up high, you see some symbols there that are gray. That's our pre-retrofit condition. And then as you go through the different colors across the rest of the plot, diving down towards the right, those are different R factors that were really different levels of retrofit. So it could have been a moderate level of retrofit, moderate strength, and then going to higher and higher strength, we were able to see the performance improve. And we had other charts that we looked at, really the same information presented in different ways. And we looked at the different performance criteria and how much drop in probability of collapse could we get from the existing condition, as you can see in black bars here, to a range of different retrofit solutions. So all of that was worked in along with the constructability, and we came up with what we thought were very simple, pre-engineered prescriptive retrofits, and then simplified engineering design methods. Speaking again to keeping it simple and having it as broadly used as possible. One of the other things that we did look at is that if you were going to go in and, for example, retrofit a cripple wall and put plywood on it, we wanted to make sure that we could connect the top and bottom of that plywood wall into the floor above and the foundation below, so that we could really get the benefit of the full strength of the retrofit. And so we developed a methodology to do that within both the numerical modeling and simpler analytical studies. And there was some limited study of that occurred in the Pure CEA project that we're going to be looking at later, where we were, at least in a couple of instances, able to confirm that we achieved our objective of making sure that the connectors were stronger and we could go to the full peak capacity of the plywood, and we could in fact go to the point where the plywood was literally falling off the structure, and our connections at the top and bottom were still in good shape, functioning as intended. Closing out, I'll just say that we did look at the new retrofit provisions in a context of what had been out there already, including in the international existing building code. There are appendix chapters, including A3, that address cripple walls, along with some other plan sets, and some chimney provisions around post-earthquake repair. We are very much in line with the other provisions out there, and we're compatible with them, but the FEMA P1100 really brings out the latest thinking regarding both the level of retrofit and the details of retrofit. And with that, I'm going to conclude and turn it back over to Justin.
Excellent. Thank you so much, Kelly. I think now we can pass control over to Morgan of the deck. Morgan Griffith is going to be talking on the ATC 143 project. He is an engineer in the Buildings and Structures group at Exponent. He was the project technical director for the ATC 143 project. So over to you, Morgan.
Great, thanks, Justin. And just give me 1 second here to take control of the screen, which I have done. Thanks. As Justin said, I'm going to be introducing the ATC 143 project. The goal of the 143 project was really to produce 2 practical guidelines for the assessment and repair of earthquake damage to wood frame buildings, primarily houses. It's fitting that I'm going to be presenting after Pang and Kelly, because it's projects like the 2 projects we just looked at that informed a lot of the guidelines that went into the ATC 143 project. The project included a team of individuals. I won't go over everyone here, but we're very grateful to the CEA for funding it, of course, and then the ATC to managing it. And then there was a project technical committee of engineers throughout California, as well as a working group of not only engineers, but of folks with various other expertise that pertains to looking at houses after earthquakes have caused damage to them. Folks from FEMA, from the insurance industry, et cetera. Well, the project ATC 143 has a long history to it. It really dates back to the 1994 Northridge earthquake. And the post-op on that experience is that we didn't do such a great job in assessing and repairing houses. This was a major earthquake, of course, in a large urban area, and there were thousands and thousands of houses to be assessed after that event. Assessments were done by insurance adjusters, by engineers, by contractors, and because of this large demand for assessments, there were individuals with a whole variety of backgrounds and expertise in evaluation of earthquake damage, some with lots of experience, some with virtually no experience. The result was inconsistency. There would be similar damage patterns to neighboring houses. One neighbor was told that the damage was caused by an earthquake. The other was told the damage had nothing to do with the earthquake. Even in cases where the experts at both houses agreed it was earthquake damage, they didn't agree at all on the way to address that damage. One expert might say that the damage had no structural significance. The other expert might say that the house was damaged beyond all repair structurally and needed to be replaced. And so that led to a lot of research following the Northridge earthquake. A lot of that research was done by an organization called CUREE that many of you are familiar with, the Consortium of Universities for Research in Earthquake Engineering. And CUREE really took on the responsibility of trying to develop a consensus document for how to go about doing these assessments and coming up with repair recommendations following an earthquake. Aside from the sort of variety of expertise in folks involved in the Northridge post-earthquake damage assessment process, we really understood that one of the big problems was there was no consensus document for how to do these assessments. And so again, that's what CUREE really tried to establish. And they did that based on research done through their member universities throughout the country, as well as expert input from people very knowledgeable about these subjects. So back in the early 2000s, CUREE published 2 guidelines that culminated from all this work. The one guideline on the left here was referred to as the general guidelines. That was intended to be a document that could be used by non-technical experts, people like insurance adjusters, homeowners, contractors, who could use this set of guidelines to repair essentially non-structural damage to houses. It was a very practical guide. It included tables, patterns of damage, appropriate repair for each of those patterns of damage. And it really went a long way in helping, again, insurance adjusters and homeowners repair damage to houses that was non-structural in nature. The goal of that original CUREE project was also to produce a companion volume called the Engineering Guidelines for technical consultants, for structural and geotechnical engineers who would be assessing and coming up with repair recommendations for damage that was structural in nature. Due to funding priorities and time constraints, only the geotechnical portion of the engineering guidelines was completed and published in early 2000. The goal of the ATC 143 project that was recently published here in July of this year was to update the general guidelines, the document on the left, the one for the non-technical individual, as well as to finally complete the engineering guidelines, to create the guidelines for the structural and geotechnical consultant engaged in these post-earthquake damage assessments. As we all know, and as we all just observed in the presentations by Peng and Kelly, there's been a lot of research that has gone on since the early 2000s when those 2 CUREE documents were published. And so the ATC 143 project attempted to incorporate all of the state-of-the-art research that's been done and all of the lessons that have been learned in recent earthquakes. So the photograph on the left here is looking at some testing that was done involving cripple walls and how they affect the performance of houses. The photograph on the right illustrates a house that was damaged due to some ground failure mechanisms that occurred in New Zealand after an earthquake there in recent years. So it was not only an updating of those documents, but it was also trying to incorporate all of the great research that's been done since those documents were published. The result of the ATC 143 projects is the 2 volumes that you see on this slide here. So again, the one on the left is the update of the general guidelines. This is the document that's intended to be used by non-technical individuals. And the document on the right is now the finally completed engineering guidelines. We'll get into that a little bit more in the next few slides, but it is the document intended to provide guidance for structural and geotechnical consultants who are assessing damage to wood frame houses after earthquakes. Documents are free. You can download them from one of two places. You pick your favorite. You can go to the California Earthquake Authority website or the Applied Technology Council website. You can also order them from ATC in hard copy if that's the way you still like to look at things. The overarching goal of really both documents is to increase the efficiency, consistency, and reliability of the earthquake damage assessment and repair process. We'd like to avoid the Northridge experience again. We'd like for engineers and adjusters and homeowners who are trying to assess and repair damage to houses so that communities can recover to be working from a common set of guidelines that discusses the implication of earthquake damage on the structural performance of the building and recommends appropriate, efficient repairs to address that damage and to restore the building to its pre-earthquake condition. That really is the overarching goal of both documents. Within that overarching goal, the objectives of the documents are to help facilitate the identification and documentation of earthquake damage, and then to develop a conceptual scope of repair for that damage. We're trying to help in the case of the general guidelines, adjusters and homeowners, and in the case of the engineering guidelines, structural and geotechnical consultants. We're trying to help them efficiently identify the damage that is earthquake related, and then to very quickly identify the most appropriate repair for that damage that is efficient and that will restore the structure. The general guidelines, in addition to advice about, or guidelines rather, for assessing the damage and repairing the damage, they also include a wealth of information about earthquakes. Information that I think is useful not only for non-technical folks, but it's also useful for technical folks that either don't have a particularly strong background in wood frame structures, or perhaps have only limited knowledge about earthquake effects on buildings. So even though the general guidelines was mainly written for non-technical folks, it has information that is useful for consultants as well. It also has a format that I think is very useful for individuals involved in repairing houses. As you see at the bottom of the slide here, it breaks the house into its main components and systematically walks through each of those components, describes patterns of earthquake damage that are common to them, and then for non-structural damage, includes repair recommendations for each of those patterns of damage. The engineering guidelines, aside from, again, fulfilling the basic objectives of giving guidance on identifying the damage and repairing the damage, also include a lot of valuable background information on common vulnerabilities for wood frame houses. So some of the vulnerabilities that Kelly went over, those are addressed in a very short, succinct section of the engineering guidelines that includes a lot of great pictures showing what type of damage can occur when we have these various configuration vulnerabilities in houses. They do a similar thing for earthquake-induced permanent ground deformation. They talk about the various mechanisms whereby ground can fail during an earthquake, again, using pictures to show what the manifestations of those ground failures look like. And then the engineering guidelines also discuss how a damage assessment is different from many of the other earthquake-related services that engineers are used to providing. And I think that's very important to understand how the ATC 143 documents fit into the larger context of documents that address earthquake damage to houses. So it's different than a safety assessment, where the goal is really to make sure that houses are safe to occupy and safe for residents to enter, but that may not be focused on damage that's not critical to safety. It's different than a document like ASCE 41, or a retrofit type document that's trying to limit damage in future earthquakes. And it's of course different than design of a new building. And many engineers that are involved in assessing damage to earthquakes might have strong backgrounds in these other contexts, but not in the context of assessing and repairing damage. And so the engineering guidelines have discussion about why this type of assessment is different and how it's different. Again, the audience for the guidelines is twofold. The general guidelines is addressing primarily damage that is non-structural. It has people like adjusters, contractors, and building owners in mind. And the engineering guidelines now is assessing damage that is primarily structural or geotechnical in nature, and it's considering structural and geotechnical type consultants. There are two different types of technical consultants that are envisioned by the engineering guidelines, and the document really is broken up so that the structural consultant can focus on the structural chapters, and then the geotechnical consultant can focus on the geotechnical chapters. But again, there's guidance for both of those individuals in the document, and there's good background information on both of those disciplines so that the structural engineer looking at a property has the wherewithal to identify potential indicators of geotechnical damage, even if that is not their primary area of expertise, and vice versa. The document, the engineering guideline specifically, does envision a basic understanding of earthquake engineering and wood frame construction. So it has a lot of great background information, but it is not a textbook on earthquake engineering and wood frame construction. It assumes a certain background in those disciplines by the user of the guidelines. The documents also are aware of one another, and we think this is a very valuable aspect of the two documents. It recognizes that most post-earthquake damage assessments will begin with the general guidelines, at least at the level of the general guidelines. They will begin with a property owner or perhaps an insurance adjuster assessing damage to a building. And we'd like the insurance adjuster and the property owner to be able to handle all of the damage that is non-structural in nature and therefore can be dealt with without the help of a technical consultant. That will free up technical consultants to focus on the buildings that really need their expertise, and it will allow those property owners who have damage that is not structural in nature to quickly perform repairs and get back to the business of recovering after an earthquake. And so the document is, the general guidelines document is sprinkled throughout with indicators that would indicate damage is structural in nature. So it provides all the guidance that the non-technical person would need to repair the non-structural damage while identifying those indicators that the damage may be structural in nature, and therefore the user of the general guidelines should engage a technical consultant that will be using the engineering guidelines. And if we look at that in the form of a flow chart, the flow chart you see on the screen here has the general guidelines on the left, and it has the engineering guidelines on the right. And you notice that the diamond in gray near the right-hand side of the left part of this flow chart says indicators of structurally significant damage. So if there are no indicators of structurally significant damage, and again, those indicators are included in the general guidelines, the damage assessment and repair process can stay on the left of the flow chart. It can stay within the general guidelines. However, when those indicators are present, now the user of the general guidelines is clued in that they need to then involve the engineering guidelines, usually through hiring a technical consultant. And then the user of the engineering guidelines is told to recognize that the results of their investigation will probably be fed back into that original damage assessment process that was begun on the general guideline side. So we also are making sure to let the engineer that's using the engineering guidelines know that their conclusions and findings will likely need to be interpreted and understood by the property owner or by the insurance adjuster to complete the overall damage assessment process. Just a quick example, the document, the engineering guidelines and the general guidelines both culminate, if you will, with repair tables for various damage patterns. And the table I'm showing on the left here comes out of the general guidelines. It is the repair table for stucco, and it lists various damage patterns to stucco that occur during earthquakes that are non-structural in nature, and it provides the appropriate repair recommendation for that damage pattern. And you'll notice that that table on the left only has about 3 damage patterns to it. These are the 3 non-structural damage patterns. If we have a damage pattern more severe than these 3, the user is directed to the engineering guidelines, and the table you see on the right of this slide comes out of the engineering guidelines. It is the stucco damage pattern and repair table for stucco, and the first part of that table includes those non-structural patterns of damage, but then it goes beyond those non-structural patterns of damage into structural patterns of damage. So again, general guidelines user can handle everything up to the 3 patterns shown on the left. If the pattern is beyond that, they are directed to the engineering guidelines, where the engineer has a variety of damage patterns and repair recommendations that are now related to potential structural damage to the building. So the documents are structured in a way that there is a good integration between the 2 users. As I wrap up here, I just want to say quickly, the repair objective of the engineering guidelines is to restore the house to its pre-earthquake condition. The document addresses the potential for code-triggered upgrades. It also addresses the potential for desirable voluntary upgrades that might address a configuration vulnerability of a particular house. It simply advises the user to separate those 3 bins out separately so that the adjuster or homeowner that's dealing with the repair can deal with those separately. And it does that, it restores the house to its pre-earthquake condition, relying on a whole variety of research that's taken place that looks at performance of various components of wood frame houses, that looks at when those elements have perhaps lost peak strength, perhaps lost stiffness in a way that might affect future performance of that element. And then it identifies repair patterns that restore those elements back to their pre-earthquake condition. So there are appendices in the document that really link the research that's been done on performance of these elements to ways to restore the building to its pre-earthquake condition. And with that, I'll just finally conclude by saying that there is a similar philosophy for the geotechnical consultant and the geotechnical aspects of the engineering guidelines that address permanent ground deformation, basically so that the building can be repaired. So the goal of the geotechnical repair recommendations and mitigation recommendations is to restore the site in a way that the building can actually be repaired. And that typically is what the property owner is concerned about. And so with that, Justin, I'll turn it back over to you so that we have some time for question and answer.
Excellent. Thank you, Morgan. Yeah, thank you very much for that presentation. So we've got a few questions here. They span all 3 projects that we just heard about. So Kelly, Morgan, and Pang, why don't you get yourselves off of mute and show us your faces just to make this a little bit more personal. Okay, so I'm gonna run down these, and in many cases I think they could be answered by several people, but I'll just call out who I think it's probably most appropriate for, and then others can chime in afterwards. So the first one, interior partitions contribute a great deal to building performance of older houses. So should we be working with building departments to discourage interior wall removal without a seismic assessment or retrofit? That seems like a good one, Kelly, for you to take, but and then at least to start off with?
That is an excellent question, and one much talked about. I think one close to Janelle's heart also, because yes, it is the entire wall structure throughout the building, whether it's called a bearing wall or a structural wall or a partition or whatever it is, it all contributes, and it is definitely something to be thinking about, I think something to look to in the future to figure out how to manage that from a building code, existing building code perspective.
Okay. Morgan or Peng, do you have anything that you want to add to that? It's okay if not.
Yeah, Justin, I'd say, sure. Yeah, Justin, I'd just say that, you know, it's a question we thought a lot about actually in the ATC 143 project as well. You know, do we only address the official elements of the lateral force resisting system when we're thinking about restoring structural performance? Or do we also consider, you know, elements of the building that might not be on that official load path if we were designing the building, but that we know contribute to the seismic performance? And we decided, in a sense, to just address all of it and to make sure that wherever that wall sheathing, let's say, for example, you know, drywall wall sheathing, wherever that damage occurs, be it on an official wall of the load path resisting system or not, we're restoring the sheathing so that its structural performance is restored. So our document addresses all of it, whether or not it's officially structural or not.
Okay, the next one, I think probably this is most for you, Morgan. This is in relation to the 143 repair reports. So just about every concrete crack was determined to be earthquake damage in the Northridge earthquake. So how does the damage assessment document handle this?
Yeah, it's a good question. So the document discusses non-earthquake causes of damage. And as probably many of you know, the vast majority of cracking to concrete is non-earthquake related. So the document discusses ways of determining whether or not that cracking was earthquake related or not. It walks through many of the mechanisms that result in cracking of concrete. The number one being the fact that it's just concrete, but it talks about things like expansive soil behavior and other ways that concrete might crack that is independent of the earthquake. And then it goes through and discusses what are those mechanisms, such as ground failure mechanisms, that can result in concrete failure, and what does that look like when that ground failure really does result in cracking of the concrete.
Great, thanks, Morgan. Okay, so this one, I think, Peng, this is for you. It's a question about, I think it's related to the red tag data, and then maybe sort of related also to the benchmarks for. But so it says, is the probability of collapse 5% or 0.5%? And the curves looked like they had a vertical axis of 0.5%.
Very good observation. If you look at the actual curve, yes, the vertical axis kind of showing like 0.5%. That plot was displaying all the raw data. The denominator was divided by all the building estimated based on census tract data, how many wood building in each census tract. There was a further processing where we actually figure out the actual number of building inspected versus just all the building in the rectangle in the census tract. So once you perform the further processing, the target came out to be about 2% for one-story wood building and about 5% for two-story and taller building. So just based on the inspected data versus the rectangle. So I think in the maybe when the wood report come up, there will be more detail. Ones can kind of look into the report.
Great, thanks, Peng. Okay, we've got a couple more minutes here. Let's see, maybe we'll get through one or two more questions. So I think this is probably mostly for you, Kelly. So are there other common vulnerabilities seen in residential construction, say other than wood light frame systems or occupancies other than single family dwellings that would benefit from prescriptive retrofits?
So there were further vulnerabilities that were identified at the start of the ATC 110 project. There were a handful of other vulnerabilities and combinations of vulnerabilities that are occurring in the building stock. And we needed to have a solvable set of vulnerabilities, a limited set, in order to move forward and come to retrofit methodologies. So there certainly are some others out there. One of the ones that is a combination that's very much talked about and prominent in the building stock is a combination of a cripple wall house and a living space over garage house, where the garage is a slab on grade, but the rest of the ground floor has cripple walls. And so there is the current retrofit provisions can be used to retrofit each of those, but there hasn't been significant study of that combination and other things like anchorage on slab on grade houses and a handful of other identified vulnerabilities.
Okay, thanks, Kelly. So I think we've got time just for one more. Morgan, this would be for you, I believe. So in your work developing the repair guidelines, were there any types of damage or damage to certain types of components that you found could really benefit from additional physical testing or other research?
That's a good question. We felt like many of the configuration vulnerabilities that are common to wood frame houses had a good sort of background of research associated with them, and some were pretty current, really. So cripple walls were addressed recently. Kelly discussed some of that today, and so it was really nice to have that to be able to incorporate into our project. The document does address some of the proprietary and, let's say, supplemental steel type retrofits that are becoming more and more common in houses today. And I do think that there could be some more research on some of those newer types of elements that are going into houses today that might benefit. There perhaps haven't been a whole lot of, cantilever column type retrofits that have gone through a major earthquake such that we understand their performance and how to repair them. So I think that, some of those type of elements could benefit from some future research, certainly.
Okay, thanks, Morgan. Well, I think we should wrap up. I just want to thank all the presenters again for excellent presentations and thank the CEA for this opportunity. So over to you, Janelle.
Well, thank you. Thank you, Justin. Thank you, Peng, Kelly, Morgan. I wanted to just tell you how much we appreciate the tremendous work that was done on these ATC projects. The CEA is getting very close to rolling out training for the FEMA P1100 plan sets and for ATC 143 that we're going to be calling the damage assessment document. So exciting to moving into implementation. We are now moving to break and we are going to be back at 11:10 sharp. So 11:10 sharp. Everybody take that really quick trip around the corner to the restroom and we'll see you back soon. Bye-bye.